Thank you all for sticking with the no power to and going through the break to listen to the presentation. So this is work that I have been doing with Josh Stokely, who is a master's student at the University of Washington. We're looking at calibrating an OpenSees layered shell element for simulating the earthquake response of walls. We're using the SimCenter QuoFem application and also design safe computing resources. And I would be remiss if I didn't add that this is building on a lot of previous work that was done in collaboration with my colleague, Professor Don Lehman, as well as PhD students and master's students at the University of Washington. The goal of this project is to use a large published experimental database to calibrate this OpenSees model for simulating the nonlinear cyclic response of planar and, probably most importantly, non-planar walls exhibiting flexure-controlled response, and investigate the use of Jupyter notebooks for modeling the building through to visualization, using the SimCenter QuoFem application, which facilitates use of design safe HPC resources and the Dakota software that is available on Design Safe for the parameter estimation and sensitivity analysis. And I guess I want to highlight the idea of using this model to simulate the cyclic response of non-planar walls. When you're talking about planar walls that are flexure controlled, it's pretty straightforward to do that simulation. You could even at some level use like a beam column type element, and we've certainly done that work. As you start to get flexure shear interaction, you really want to go with a planar type model so that you can represent that flexure shear interaction. And then once you go to non-planar walls, you really need that planar model so that you can look at what's happening in corners and make sure that you're getting that good representation of the flexure shear interaction. So using this layered shell element is particularly important as we start thinking about non-planar walls. Why do we want to look at reinforced concrete walls? They're very commonly used as lateral load resisting systems in seismic regions. Here's a picture of our new computer science and engineering building next to our old civil engineering building. It's got a concrete core wall in the middle. As we've been talking mostly about bridge systems, you also do see walls in existing bridge buildings. And so there is a value in having these planar shell elements that we can use to simulate walls, especially older walls, again, where you may have that flexure shear interaction and want the shell element as opposed to just a beam column element. The nonlinear response models used currently to design new and evaluate existing walls can be improved substantially, especially for building systems. They're again typically using walls that decouple the flexure shear response. We haven't done a lot of work with those models and looking at how they actually simulate the response of core wall systems or non-planar systems. And so I think there's a lot of opportunities there. And there are also opportunities for using the NEARI design safe resources and SimCenter tools. This is the experimental data set that we're using from model calibration. This data set was published by Shige et al. In 21. It has 142 walls from 32 different research programs. For this particular project, we're just using 48 of the walls that are for planar walls. The remainder of the 142 are T-shaped, C-shaped, et cetera, and that'll be sort of this second phase of this research project. And I wanted to show on the right here, these 48 planar walls that are exhibiting flexure controlled response have 3 different failure modes. There's a compression buckling failure mode where you're seeing the wall lose strength due to buckling and compression failure on the left corner there. There's some walls that exhibit tension failure, and there's one in the middle there that's sort of emphasizing this large flexural crack. This is where bars are fracturing, and so it's a flexural tension failure. And then at the bottom there is one that is still a flexure-controlled wall, but you're seeing a lot of flexure shear interaction, and that reduces the deformation capacity substantially. And so those are failure modes that we should be able to pick up in this layered shell element. This is showing some statistics for the data set that we're looking at. These are some parameters that we found in the past to really control the behavior of these wall systems. Let's see if I could. Where do I want this? Let's take it up here. These are bar charts that just show the number of walls that meet these certain parameters. So we've got aspect ratio, height over length. The taller these walls are, the more flexure dominated they tend to be. Max shear demand. You can design walls up to 8 to 10 roots F prime C, but we have very few tests that are actually in that range. It requires a lot of capacity in your experimental lab. So most of the walls are in this sort of 2 to 5 roots F prime C range. We found in past studies that how slender the wall is in aspect ratio has an impact on whether it's flexure controlled or there's flexure shear interaction. As you start to get into this cross-sectional aspect ratio CSAR of 10 to 15, that's where you start to see more flexure shear interactions. So most of these are going to be really flexure dominated, but there are some that are longer and skinnier where, again, this layered shell element is going to help us represent that behavior. The axial load range is pretty modest, up to most of these are in 10%, 20% F prime CAG. And then we're seeing most of the walls are exhibiting CB, which is that compression buckling failure. We've got about 10 that are doing buckling rupture, and then only 1 or 2 that are in the compression shear. That was the wrong direction. This is what the model looks like. It's an OpenSees layered shell element. It was developed by Liu et al. Published in 2015. The way that we're modeling it is a whole bunch of these shell elements. So each of those little 4 nodes is one of the layered shell elements. They're layered in the plane for these planar walls. There is not an ideal way of meshing this out in OpenSees, and so we're actually dropping off the cover concrete on the left and the right of this wall, and then we're putting in truss elements at each of those nodes to represent the longitudinal steel, and then the horizontal steel we're smearing as a smeared layer in that layered shell element. So we're not smearing the vertical, but we are smearing the horizontal steel. One nice feature that one could envision adding to OpenSees would be the ability to embed reinforcing steel wherever you wanted in a concrete continuum. The reinforcing steel is modeled just using the Steel O2 model in a truss type element. This is some more information on the layered shell element. There's a plane stress concrete constitutive model also developed by Liu et al. That we're using for the concrete layers. There's a confined concrete layer, an unconfined concrete layer. And then there's some tools that essentially smear that horizontal steel. So you're going from a truss type element to now a smeared layer in the shell. The concrete constitutive model uses a 1D constitutive model for concrete, and then it rotates it normal to the crack surface. So you've got tension and compression normal to the crack surface, and then you've got a shear stress parameter on that crack surface. And so 2 of the things that we are calibrating for this is the shear transfer on the crack surface, this beta value that you can see in that in the purple on the bottom, and then terms that we've been using in recent studies are the crushing energy and the fracture energy, which are the blue area and the red area in that plot up on the top right. And that determines essentially the strain at which you see strength loss. And so we do it as an energy-based value to calibrate it. So those areas are if you look at the bottom right there in blue, it says the area under the compression softening curve is GFC, which is the crushing energy divided by the length of the element. And since we're using an energy term dividing by the length of the element, you don't have any mesh sensitivity. So I can change the element size, and because I've got that LE term in there, I get consistent results as I start to refine my mesh. So part of what we're doing in this initial study is calibrating what is the appropriate crushing energy, what is the appropriate fracture energy, and then what is the appropriate shear friction term on that crack surface. And those are the 3 parameters that we want to calibrate. For the steel material model, we use the parameters that are defined by typical test data, the elastic modulus, the yield strength, the hardening ratio, and then terms associated with cyclic response. So we're just taking that from standard practice. What we want to do is use the compression failure strain at which the concrete crushes. That's where we say that the steel also buckles. So if all your concrete around a steel reinforcing bar is crushed, the bar is going to buckle and lose strength. And then the tension fracture strain is also a calibrated parameter. This is just sort of emphasizing that we're using these Jupyter notebooks to do all of this work. There, I think 3 of the initial notebooks that build out the models, run the OpenSees analyses, are published in this set of Jupyter notebooks that Design Safe is published. So if you want to take a look at those are available. They build the models, run the simulations for an individual wall. Specifically, the notebooks pull data from the Shugay database that they create the OpenSees model for each wall. They run the analysis. They process the output, producing load displacement graphs, the cross-section element strain graphs, some crack pattern movies, and some stress strain movies. And then they also compute errors that go into the QuoFem software. This is just showing some of the sample output. Here's a load displacement plot on the left top for one of our walls. In the middle, you can see these Jupyter notebooks produce the strain histories for individual bars that are at the bottom of the wall. So this is a bar on the left and on the right, and a concrete element on the left and the right. And then we created some visualization of data. And so you're looking on the top right at concrete stress strain movies. And I don't think the movie actually got embedded at this point. Oops. So, oh my goodness, this is challenging to go back now. But there are a series of visualizations like this that show stress fields and strain fields and damage parameter fields. As we move forward, here's another one of the walls. Again, you can see all the data and then the simulated crack pattern. So this is a wall that is a compression buckling wall, but it's still very flexural dominated. So you can see that the cracks that we're seeing are essentially horizontal. So those are forming initially when the wall goes into tension at these extreme fibers, and then in the interior where you're getting sort of diagonal cracking that's more associated with the shear, more dominant shear response in the interior of the wall. These are some of the stress fields. We've found that looking at the minimum principal stress is a really good way of assessing what is happening with the concrete, because that's the point at which the concrete is going to crush. And so this is a wall that's exhibiting a compression buckling failure. So this is the vertical stress field, and then this is the minimum principal stress field at the nominal flexural strength of the wall. You can see that there's a significant amount of compression in the bottom right corner, and then this is just vertical stress. So you're seeing you're seeing some tension stress over here. It's very low. It's cracked probably at that point, and it's getting really close to the 0 point. But then when you look at the minimum principal stress, you see there's almost nothing up here where it's in shear or in tension. And then again, this fairly high minimum principal stress at the right corner. When we get to the failure point, you can see that over here, the maximum magnitude minimum principal stress is in the interior of the wall, and that this has actually already crushed over here, which is why we're seeing the lower minimum principal stress here. So this is indicative of a compression type failure where the concrete is crushing on the this far compression point. I just pulled these out of a cyclic movie. The analyses are cyclic, but this is just a particular point when we're loading it essentially to the right at the failure point. And so that is how we determine that this is actually a compression buckling failure, because you're seeing that that crushing of the concrete on the far right or in that extreme compression zone. This is a wall that exhibits a bar rupture type failure. You can see that these data look pretty similar to the data that we saw before. I guess if I go back to here, this is a compression buckling failure. This is showing the stress strain response of an extreme concrete fiber, and you can see how the concrete fiber has gone up to its compressive strength and then gone to zero, indicating that crushing of the concrete. On the right side, it hasn't quite crushed. This is crushing on the left side. And then if we go to this buckling rupture failure, you can see that this concrete hasn't actually got down to the point of zero strength, so it hasn't actually crushed completely. And the steel is actually fracturing right here. And that fracture is a calibrated fracture. So this one has been calibrated to fracture at the right points. The crack pattern looks pretty similar to what we saw for the compression buckling. But when we look at these stress fields, here's again the vertical stress and the minimum stress. When you look at this point at failure and you look at these minimum compressive stresses, you can see that this looks pretty consistent across this bottom. There isn't this region over here where the stresses are lower that would be indicating crushing. All of this concrete is basically carrying its maximum compressive strength. And so that's how we say this is not a compression buckling failure, because we're not seeing that crushing of the concrete. So that's the model that we're working with. Those are two examples. So now we're going to kind of go on to doing the sensitivity analysis and the parameter estimation using QuoFem. So QuoFem, as Greg Dearland was talking about, is an application that's been developed by the Sim Center. It does both sensitivity analysis as well as uncertainty quantification, and then calibration and parameter estimation using a variety of different methods. You can run it on your desktop, or the way we use it is actually to launch jobs on TAC resources. Just noting that you can download it. So the parameters that we are looking at in our sensitivity analysis are the concrete shear retention factor. That's that shear retention on the crack surface. You probably don't want to look at that, or hopefully you don't. The concrete crushing energy for the confined concrete. We have a baseline unconfined crushing energy that comes from testing of cylinders that people have done in the laboratory many years ago. We're saying, well, what's the crushing energy for confined concrete? So we're calibrating that. And then reduction in the steel tension strain capacity associated with rupture of the steel due to buckling and fracture. So those are the three parameters that we're trying to calibrate. And the error factors we're using, or the error measures, are strength, deformation capacity, and cyclic response. I would note that we have done this previously with other types of models. So we've done this with finite element type models and calibrated these values for finite element type models. We've done this with fiber beam column elements and calibrated these values, not the shear retention factor for the beam column elements, but we've calibrated these previously and been pretty successful in getting values that are a single value across a large data set. So we're pretty confident that we can do the same with this fiber shell element. This is just looking at a shear retention value, which is again that shear on the cracked surface. If you have a really low value, on the left there, you have very low deformation or drift capacity. On the far right, we have a very large value that starts to increase the strength because you're getting a lot more shear friction on that crack surface than you really ought to. In the middle is sort of this perfect value of 0.095. This is looking at the crushing energy. On the left, we have a low crushing energy for the confined concrete. It's failing prematurely. On the right, it has too much deformation capacity. In the middle, it's just right. So we've done some initial analyses. These are really preliminary, so it's not clear whether or not we're going to be able to get a constant value, or we're going to have to make it a function of some design parameters. And then we've moved on to also looking at using some of the tools that are available in QuoFem to do the parameter estimation for us. So first, we're kind of sensitivity studies, run 10. And this one is looking at using some of these different tools. Thus far, we've found that we need to use a method that is not gradient-based. We just can't use a gradient-based method to do the parameter estimation. So next steps are to finalize the calibration and to compute some error functions for our validation data set. We split up our data into a calibration set and a validation set. So that is what I will present on next year. And I think at that point I've used up my time, so I will offer to answer questions at lunch.
Well, let's wait, maybe there'll be time at the end of this session because I think we're still short of one speaker.
We have the.
Oh, no.
Thanks.
Thank you very much.